Hi, and welcome to our third lecture grab. And I'm glad you're on time because this lecture grab, sorry, really bad pun, is all about timing. We're going to be talking about dating and the fact that timing is everything. Okay, now that's a bold statement. What I mean is timing wraps up everything, doesn't it? Yeah. A lot of time in quaternary science, we kind of know what happened. We just don't really know when it happened. So timing has become a really big thing. And that's exactly why I got into luminescence dating, because really timing, you're never going to be out of a job if you're doing dating. Okay. So let's have a look at the dating techniques. Now, this is a bit overwhelming, this page. There's a lot of dating techniques here. But they're really divided into numerical age, and that's the one when we get an age of 20,000 plus or minus 1. So we actually get a number, okay? Then we have age equivalent, and that's when we're sort of like saying, well, we dated this tephra to 70,000, so whenever I find this tephra, I know it's 70,000. So that's like age equivalent, okay? And then we have relative age, and that's all about when we know about certain chemical processes, we kind of know roughly how long they take, and we can do dating like that, okay? So that's three very different ways of dating. I'm involved in the numerical age dating, and there are two different types of numerical age. There's radiometric dating, and then there's incremental. Now, incremental is things that accumulate over time. So I've got a picture here of, let me see if I can get my pointer. This is a tree ring, and this is what we call dendrochronology. So they're actually using tree rings for dating, okay? Or things like varves accumulating in a lake, okay? So anything that increments and that you can count, all right? Numerical aging and radiometric aging is all about how things decay over time. Okay, so we're looking at atoms and how they decay over time. And as they decay, or we know how they decay and how long they decay. So if we work out exactly where we are on that decay chain, then we can work out how old something is. Okay, so there's lots of different types of radiometric dating. The big three are radiocarbon, uranium series, and luminescence dating, which I'm going to talk about in a minute, okay? So radiocarbon dating is dating anything that was living. So if it was living at any time, then we can date it with radiocarbon. If it was never alive, we can't date it with radiocarbon, okay? So living organisms absorb CO2 in their tissue, okay? And they're absorbing a radioactive form of CO2, which is carbon-14, within the system as well, okay? But because it's being replenished all the time by all the new carbon, then it doesn't decay in any way. But when that organism dies, that replenishing is not happening anymore. So the carbon-14 that's in the body or in the living organism will start to decay. And the decay we know very well, radiocarbon decay, and we can then work out where it is on that decay path to work out how old it is, okay? Now, uranium series isn't dating anything organic, okay? It's inorganic, but it's based on the decay of uranium and thorium. Now you can see here, there's a very complex decay chain here. It's not really complex, it just shows you the path that the decay goes down, all the way down to stable lead at the bottom here. So uranium and thorium, we're just working out the ratio of uranium to thorium and whereabouts it sits on this decay chain, and each point of the decay chain, we know exactly how long it takes to get through that decay, okay? So uranium series is used on things like flowstones and stalagmites and stalactites, so speleothems. Remember the growth curves we were looking at last lecture grab? And also coral as well. So it's used a lot, uranium series, just like radiocarbon, and we're going to talk about luminescence in a minute, okay? Age equivalent, I've talked about a little bit already. Things like tephrochronology, I know how old this tephra is, so whenever I find that, I can do fingerprinting to show that it really is the same tephra, and then I've already got an age because we already know when that volcanic eruption occurred, okay? Same with paleomagnetism as well. We know when the Earth flips its paleomagnetic fields from north to south, so we know that it flips over time, and we know when those flips occurred. So if we have a look at a rock and we can see it's got a different orientation than what we've got currently, then we know it's at least 780,000, because that's when the last time that the poles flipped. Okay. And then relative age, things like amino acid racemization, chemical processes are occurring. We know how long they take, and then we can sort of compare relatively with where it is on that decay. Okay. Now, what are the prereqs for dating? What do we need to know? Okay. So dating is a time-dependent quantity that we can actually measure, but we need a clock. We need a clock that can measure, and we need to make sure that that clock is reset to 0 before it starts measuring. Otherwise, we're not really going to know what's going on. So with radiocarbon, the clock is reset to 0 when the organism dies. Okay. With luminescence, the clock is reset to 0 when the quartz or feldspar grains are exposed to light. Okay, but I'm going to talk about that in a minute. Now, when you're dating, it's really important that you have a direct association between the material that you're dating and the thing that you're trying to date. Okay, so down here is an example. We've got some artifacts in a sediment here. Now, we've got a flowstone, which is, like the stalagmites and stalactites, secondary carbonate deposit, and it basically forms over the top of sediments. Okay, caps everything in. It's very, very useful. Okay, now if I want to date these artifacts, if I date this flowstone over the top, then that gives me a minimum age for all the artifacts below. The artifacts below must be older than this flowstone age. Okay, so that's what I call a direct association. All right, over here, this example here, look at these stone tools here. We've got rock here, and we've got a stalagmite that's grown on the top of the rock. Okay, now, and then, so obviously that was precipitated first, then the sediments built up with the stone tools in it. If I date this speleothem, it doesn't tell me the age of the stone tools. It gives me what's called a maximum age. So these must be younger, but they could be thousands of years younger. So this is not what I call a direct association. All right. When we're talking about age estimates, we always have a plus or minus. Okay. So it's not 20,000. It's not just 20,000, it's 20,000 plus or minus 1. So it could be as low as 19 and it could be as high as 21. Okay, so don't just look at the median age, which is the first number. Take into account the actual plus or minus. Okay, so let's have a look at precision, accuracy, and age range. Now look, down this line here, this is the true age. 10,000 years old is the true age, the real age. Okay, and you can see here, technique A is not very accurate. Okay, so it's quite far away from the true age. It's not very accurate, but it's very precise. See, the error bars are quite small, so it's quite precise, but it's inaccurate. Okay. Option B here, you can see it's accurate because it's got the right age, but look at the precision, very low precision. Okay. So C is the winner. Hooray! Because it's very accurate and also precise. So don't get confused. Accuracy and precision are two different things. In normal English, they're quite similar. But when we're talking about dating, they are different. Now, if you have a look, I'm kind of obscuring this picture here a little bit. But you can see there's a long time range here. You can see all the different age ranges. What I want to show you, one really important one, is radiocarbon. See, radiocarbon fizzles out about 40,000 here. Can't date any higher than 40,000. 40, pushing it to get to 50 with radiocarbon. And look at luminescence. Woo! We can go much further past that. So that's really important. Okay. Then you've got things like uranium series clogs out about 50,000. Fission track just goes on. And so does ESR as well. So you can see there are different age ranges, and that has to be taken into consideration when you're thinking about what you're going to date. So what is luminescence and how can we use it for dating? So here we have some sediments here, quartz grains or feldspar grains, and they're being transported. So they're being blown in the wind, okay? And you can see there's the sun there, nice and bright. It's called what we call bleaching. It's removing the luminescent signal. So as we go over time, see how it's getting lighter? We're losing the luminescent signal. No expense spared on the graphics. And these bleached grains, so they have no luminescent signal in them, are being deposited in the sediments, okay, in the cave sediment. And over time, these grains will start to accumulate signals. So they're starting to get some luminescent signal in them. Now, if I grab one of those grains and I take it back, not just one, obviously, quite a few, take them back to my lab and I have them in lovely dark red light conditions, which keeps the signal safe, something like that. And if I shine light at it, which is OSL, optically stimulated luminescence, or if I heat it, which is the thermoluminescence, it gives off light. And the light it gives off is called luminescence. And you can see these are quartz grains all luminescing, okay? If I measure these quartz grains using what's called a photomultiplier in my lab, I get this kind of thing happen. Woo! Like that. That's the luminescence coming out. Lots and lots of luminescence coming out here. And it slowly decays exponentially until there's no luminescence coming out down the bottom here. Okay, so the reason we use luminescence is because quartz and feldspars, you basically find them in every single sediment anywhere in the world. I defy you to find me a sediment that doesn't have either quartz or feldspar or even both, okay? So pretty much, if there's sediment, we can date it with OSL. And that is why luminescence is such a fantastic technique. Obviously, I'm a little bit biased because that's my technique, but I think it's incredibly useful, okay? Now, it's all about crystalline structure. I don't even know much about crystals. Maybe you like to use crystals for your healing energy and all that kind of stuff. But basically, crystals contain defects. And these defects are what we call traps, okay? Now, this is a trap here, okay? What happens is ionizing radiation, so things like thorium, uranium, and rubidium, which you find naturally in all soils. We're not talking like radiation that's going to kill you here. It's found in all soils, okay? When this energizes electrons, here's my little energy diagram here, it energizes electrons, so electrons can shift across this energy field here within the crystalline structure, and they bomb around within what we call the conduction band here, and they eventually come down and they get caught in traps, okay? So this is the whole principle of luminescence. Now, people get a bit caught up with all these terminology and words. Don't worry about it. All you've got to know is that it's a light-sensitive signal. It builds up whilst it's being buried underground, builds up by all these electrons getting caught in traps, okay? Let's go to the next one. We'll see what happens then. So we've natural radiation energizing all of these electrons. We've got them caught in traps. So here is our little electron caught in a trap. Now, if we shine light at this electron in the trap, it's going to get excited and go back up into the conduction band, come along and come down into a luminescent center. And when it's in a luminescent center, it gives off light. And this is the luminescence that we're measuring in the lab. Now, obviously, the more electrons that you have stored, the more light it's going to give off. And obviously, the more electrons you have is how long it's been sitting there since burial. So the more electrons during burial that build up and then give off light will give off more light. So it's proportional to how long it's been accumulating. So just think of it like, you know, little balls accumulating within these traps, and then suddenly we expose it to light and it gives off light. So it's a little bit confusing, all we're doing by exposing it to light is energizing it. So the electron can jump out and become light itself, if you know what I mean, okay? Now, this light that's happening here, this can happen in the lab when we're measuring it, but it can also happen in nature, okay? And this is what we call a zeroing event. Okay, so do you remember how we showed the sun and we showed the luminescent grains losing signal? This is what we call the bleaching. And bleaching is very important. Okay, so this is luminescence in nature. Okay, so we got the naturally occurring radiation in the soil. So we get a build-up of signal. So this is electrons building up inside the traps. Then we get a bleaching event, so we get it. The signal is reduced all the way down to zero. So remember, this is our clock, okay? We're setting the clock, the stopwatch, back to zero by the bleaching event or the sunlight event, okay? Now that it's been set back to 0, we have no electrons in the traps, okay? And this is what we call our last depositional event. Now our electrons can start to build up again because they're buried in a cave or in a river terrace or in a sand dune, and they start to build up. And then we take our sample, sorry, these are the electrons building up, and we take our sample here, and we know that the age is equivalent to how many electrons or how much light we've accumulated since it was last buried. Okay, so we're not dating the age of the sediment, we're dating exactly when the sediment was last exposed to sunlight. And when you're talking about geomorphology, you're talking about deposition in a cave or deposition in a river terrace, that's the time that we wanna know. Okay, so when we're talking about the age, there are two things that we need to work out. The first one is right here, which is the sampling. So we sample the luminescence in the dark, okay, and that's what we call the equivalent dose. How much luminescence we get from our measured sample, and we divide this by the luminescence actually in the soil, and this is what we call a gamma spectrometer, and this is measuring how much radiation we find in the soil. Okay, now radiation comes from beta, alpha, and also gamma, and also from cosmic rays. So this natural radiation that I was talking about at the beginning that energizes the electron, so if we have how much luminescence we get and we divide that by how much radiation in the soil, that actually gets us our age. So it's a very long and difficult process, but the actual final equation is very easy. Okay, so if we heat it, it's called TL. If we shine light at it, it's called OSL, okay, optically stimulated luminescence, or even IRSL, which is infrared stimulated luminescence, okay? Why do we do that? Well, if we measure the natural signal in the lab, that's our natural, that's how much luminescence we get from our sample we've just collected. And then if we regrow, oops, is that coming here? If we regrow the luminescence by stages, so these are what we call dose points. So I get artificial radiation from the lab, and we give the sample these doses and see how much luminescence I get. So basically we're just regrowing the luminescence in the lab, okay? So this natural signal then we can interpolate onto this line and read down, and we can work out exactly how much the light represented by dose, and the dose is what we call in grays, okay? So how much of this radiation dose was accumulated by the sample over time. Now the reason I'm telling you all this is because we do actually play around with luminescent signals in the workshop, okay? Oh, there we go. Didn't have to draw it at all. There's all the luminescence. Fantastic. Now, what's the advantages for sediment dating? Okay, we're assuming that all the grains have been exposed to light over time. Okay, and that's great for aeolian samples, which are blown around all over the place. Okay, but what about cave sediments? All right. So, oops. So basically, if that'll go back. No. So we get bleaching effect of sediments over time. But what happens if we've got a cave sediment and we've got our bleached samples that have been reset to 0? And I don't know if you saw that graphic there, but basically what happens then if we get quartz grains from the sediment above in the rock shelter dropping down into the sediment, okay? That's going to cause all sorts of problems, okay? Some of them are really reset and represent the amount of time since it was last exposed to sunlight. And these ones, these dark red ones here, don't represent that because they've just fallen from the cave roof. So how do we pick this apart? We do this by what's called single grain measurements. So rather than measuring lots and lots of grains on the disk to give an age, we measure individual grains. And they look a little bit like this. These are individual grains of quartz in a disk, and we can fire a laser at individual grains. This is what we call single grain OSL, and it can tell me how much signal that grain has. Now, if some of those grains have been exposed to light before they were buried and some of them haven't, I can separate them out because I've measured each grain, okay? And this is why single grain dating has really revolutionized everything. So do you remember I was telling you about that rock shelter with the grains that dropped in? Now, this is Jimmie rock shelter in northern Australia. Originally, they thought the age of the sediments, which had stone tools, was over 100,000 years ago. And they thought, wow, you know, humans have been in Australia over 100,000 years. But it wasn't until they did single grain dating that they realized that you've actually got contamination from above these grains that haven't been reset to light. And it's making it much older than it really is. Now, using that technique, it's revolutionized things like artifact dating, megafauna dating, sediment mixing in Blombers Cave in South Africa. So these are all amazing examples of how using single grain dating has really revolutionized the technique. Other examples of luminescence, you can date dune stability, tsunami deposits, downcutting of river. There's so many applications to luminescence, and this is why it's so widely used. Now let's just very quickly compare luminescence dating with other dating techniques. Now this is an example of Devil's Lair in Western Australia, a megafauna site, which contains evidence of modern humans, artifacts. Now when it was originally dated, it was dated to 40,000. It was dated radiocarbon, and it was dated to 40,000. In fact, everywhere in Australia for a long time was dated to 40,000. And they were like, well, that's it. Modern humans arrived in Australia at 40,000, no earlier. But it wasn't until we started applying luminescence dating that they started to realize that there was a bit of a problem. So here's the radiocarbon ages. So this is age along here, and this is depth. Now, as you go deeper, you can see the radiocarbon ages don't get any older. So there's a lot more accumulation and a lot more age here, effectively, but they're not getting any older. Now, if you look at the luminescence, these are conventional carbon-14 ages. If you look at the luminescence dating, so here's 40,000, okay? Let's look at the luminescence. We'll get there in a minute. Now, what they realized when they looked at the luminescence, and the luminescence is, it's not highlighting for some reason, I'm gonna go do it myself. Look at the luminescence ages. They're getting older and older all the way down section. They're getting much older than 40,000. So they afterwards realized that we're not looking at the age of humans arriving. We're actually looking at a radiocarbon barrier. We're looking at the top level, upper limit of a dating technique. Okay, so once we applied luminescence, we could see that actually it's not modern human arrival, it's actually a barrier from radiocarbon. And that's why we've been redating a lot of sites that were dated with radiocarbon with luminescence, and it gives us much older ages. So now we know that the earliest people actually in Devil's Lair in Western Australia is more like 47 to 48,000 rather than 40,000. So that's really changed the game.